So here's where we left off. And continuing on with part 2. So saponification, soaps are made by heating with sodium hydroxide, a fat or triester glycerol. This will cleave that ester bond to form the sodium salt of a fatty acid, which is a soap and triglycerol. Hydrolysis of amides. You have amides in the presence of protonated water will yield carboxylic acid and ammonium. And so they're hydrolyzed to carboxylic acid under acidic conditions as well as under basic conditions. Here's an example. In the presence of sulfuric acid, will generate this acid and methylammonium sulfate. Basic hydrolysis of amides, so what happens is nucleophilic attack, electrons go up, forming the tetrahedral intermediate, and then electrons will come down and kick off the NH2, which will then deprotonate, forming the carboxylate and NH3. Under acid hydrolysis, first step is protonation, and then water will come and attack, quench that positive charge, forming that tetrahedral intermediate. Then water will deprotonate, neutralizing it, and then allowing for the rest of the reaction to occur. Now the amine will pick up a proton, making it a good leaving group so that electrons from the oxygen come down and kick it off. And then to neutralize that positive charge, it'll deprotonate to form the ammonium and the carboxylic acid. In terms of nitriles, nitriles can be hydrolyzed in the presence of base to generate the primary amide, and then another equivalence of base in water to generate the carboxylate and ammonia. So heating with aqueous acid or base will hydrolyze the nitrile to the actual carboxylate ion or carboxylic acid. And again, one equivalent will lead to just the amide. Base catalyzed hydrolysis, so here nucleophilic attack, electrons go to the nitrogen, then the nitrogen picks up a proton to generate the enol of the amide. So this will tautomerize, in which you have electrons from your oxygen come down. This goes over here. This will generate C double bond O, H plus, NH with a negative, and so that will pluck off the hydrogen, neutralize it so that you generate the actual amide, NH2. In esters can be reduced in the presence of lithium aluminum hydride, generating the primary alkoxide, right, from one side and then the other side, and then in the protonated water generating the alcohols. So here you're going to get 2 alcohols, right, from this half and then the other half shown here. And the mechanism is, here's lithium aluminum hydride. Hydride donates, nucleophilic attack, electrons go to the oxygen, tetrahedral intermediate, in which electrons from the oxygen go down, kicking off the alkoxide and generating the aldehyde. Another addition of a hydride goes in, electrons go to the oxygen, forming the tetrahedral intermediate, and then that gets protonated to form the alcohol. You can reduce acyl halides into aldehydes using a lesser or a milder reducing agent, such as lithium triterbutoxide aluminum hydride. And so, right, you can take an acid chloride down to the aldehyde. So the other mild reducing agent is diisobutyl aluminum hydride, also known as dibal or dibal H. And it can take esters now down to the aldehyde. But step 1 would be the dibal followed by hydrolysis. Reduction of amides to amines. Here are your primary, secondary, and tertiary in the presence of lithium aluminum hydride. Subsequent with water, you'll generate primary amines, secondary, and tertiary amines. So that's lithium aluminum hydride reduction. In that reduction, here's your first step, nucleophilic attack of the hydride. Electrons go to the oxygen. Then electrons from your nitrogen go, and then this leaves to generate the imine salt. Then another hydride attacks, electrons go to the nitrogen, generating your amine. Reduction of nitriles can be done in the presence of hydrogenation under catalytic, here's platinum, or lithium aluminum hydride, followed by water to generate your amine. Organometallic reagents, so if you have an ester or an acid chloride and two equivalents of either organolithium or two equivalents of Grignard reagents, it'll replace, you have two of these come in, form the alkoxide, and then in the presence of protonated water form the alcohol as expected. So here's the mechanisms. Here's nucleophilic attack. Electrons go to the oxygen, tetrahedral intermediate. Now electrons on the oxygen come down, kicking off the alkoxide, forming the ketone. Once the ketones form, another equivalence of the Grignard comes in. Electrons go to the oxygen, tetrahedral intermediate, but then this becomes protonated to form the alcohol. Important thing to note is that Grignards add to esters and acid chlorides to give tertiary alcohols with one group from the ester or acid chloride and two identical groups from the Grignard. Formate esters will give secondary alcohols with hydrogen from the esters and then two identical groups from the dialkyl cuprates. So dialkyl cuprates react with acid chlorides to generate ketones. Dialkyl cuprates are also known as Gilman's reagents, and so shown here as an example. Nitriles can react with Grignards, and here's an example where nucleophilic attack, electrons go to the nitrogen. This forms an imine salt and then becomes protonated in the presence of protonated water. And so once it generates the imine, you have acid hydrolysis, in which first the nitrogen gets protonated, and then the water comes in and attacks and does its thing to generate the ketone. So we've talked about this reaction before, so go back to your notes to do the full mechanism. Synthesis of acid chlorides, that can happen by reacting with thionyl chloride or SOCl2 or oxalochloride or COCl2, and essentially we've seen this, and the mechanism we've seen in the previous chapter. So acid chlorides react with water, generate the acid, react with alcohols, generate an ester, react with amines to generate amides, and reacts with carboxylic acids to generate anhydrides. Acid chlorides can also react with two equivalents of Grignard reagents and followed by water to form the tertiary alcohol, or organocuprate or Gilman's reagent to form the ketone. Reduction via sodium borohydride or lithium aluminum hydride forming the primary alcohol, at least subsequently worked up with water to form the primary alcohol, and then the milder reducing agent to generate the aldehyde. Friedel-Crafts acylations we've talked about with benzene and the presence of aluminum trichloride as your catalyst, and then work up with water to generate your acyl benzene. Now again, depending on the substituent around the benzene, that will dictate whether it's ortho, meta, or para directing. In this case, we have methoxy. This will be ortho and para directing, and will generate this as the major product. General anhydride synthesis, acid chlorides with carboxylate, that allows direct attack, right, forming the tetrahedral intermediate, then electrons coming down and kicking this out to generate your acid anhydride. So if it's not a carboxylate but the carboxylic acid, you can add pyridine to help deprotonate the acid and form the carboxylate to allow for the reaction to occur. Here's just acetyl chloride and the carboxylate, so this happens directly. Anhydrides react with water to generate acids, right, on either side, right, because this is anhydride here, a symmetrical one. In the presence of an alcohol, will generate an ester, and then in presence of an amine, generate the amide, again, with the other side being the carboxylic acid. Friedel-Crafts acylation using anhydrides, so anhydrides can be used and undergo Friedel-Crafts acylation using aluminum trichloride as the catalyst. And so here you'll have, this is cyclic anhydride. So cyclic anhydride allows for only one of the acid groups to react, leaving the second acid group free to undergo further reactions as shown here. Acetic formic anhydride. So if you have acetic formic anhydride, the formic group, is the more reactive carbonyl. As a result, when you have it react with alcohols, it'll attack over here. Electrons come up, electrons go down, and then kick this off. So same here, this will react in this carbonyl and then kick this out. Synthesis of esters, so you can have acid and alcohol in the presence of protons to generate your ester and water. Acid chloride and alcohol, this will generate ester with HCl. Anhydride with alcohol in the presence of acid, generate ester and the carboxylic acid. Ester and alcohol, either in the presence of acid or our base, will generate ester and alcohol. Acid in the presence of diazomethane, which we've seen in prior chapters, will generate methyl ester and nitrogen gas. Esters can react with water in the presence of acid or base, generating the carboxylic acid. Can react with alcohols in the presence of acid or base to generate the other acid. This would be a transesterification reaction. And the reaction with amines to generate amides, reaction with lithium aluminum hydride followed by water workup to primary alcohol and the other alcohol from the other side. Grignard reagents will attack two equivalents to generate your tertiary alcohol, and then Diebol will generate the aldehyde at the end. Formation of lactones, so if you have OH and carboxylic acid in the presence of acid, this will generate a ring. So 5 and 6 membered rings are favored for lactones. For larger rings beyond 5 and 6, in order to generate the lactone, you actually try to remove the water to shift the equilibrium toward the product. Reactions of amides in the water in presence of acid or base will generate acid, the carboxylic acid that is, and amides in the presence of lithium aluminum hydride followed by water workup will generate your amine. Primary amides in the presence of POCl3 or P2O5 will generate nitriles. This is a dehydration reaction from this chapter. So again, here's your primary amide in the presence of phosphorus oxychloride or phosphorus pentoxide. This will dehydrate to form the nitrile. Formations of lactams. So if you have an amine and carboxylic acid within a ring, and it's a 5-membered, you can form 5-membered ring, which would be gamma butyrolactam in the presence of heat. If it's gamma, right, so this would be 6, this is gamma, this is delta, 6-membered lactam to form gamma valerolactam. And so this is all done in heat to generate that. Beta-lactam. So here are examples of beta-lactams. They're usually reactive 4-membered rings shown here in each of these series. And they're capable of acylating a variety of nucleophiles, which we'll show in the next slide. They're found in penicillin, shown here, cephalosporins, and carbapenems. And the mechanism is that the nucleophile comes in, electrons go to the oxygen, and then when the electrons from the oxygen come down to form the carbonyl, this will cleave and electrons will go to the nitrogen, generating that joined nucleophile to the actual lactam. Action of lactam, so you have enzymes. Enzymes with OH from serines or threonines will attack, right, that electrophilic carbon center. Electrons will come up. And then electrons will come back down. I'll show that to you. And then this will cleave, right, to form a conjugated enzyme lactam conjugate, and as a result, the enzyme is now inactivated for the synthesis of cell wall protein, and that's how actually beta-lactam antibiotics works against bacteria. So in terms of synthesis of nitriles, you can take primary amide and react it with POCl3 or P2O5, as we've shown before. That'll generate nitrile. Here's alkyl halide with sodium cyanide to generate the nitrile. Here's the diazonium salt in copper cyanide to generate the aryl nitrile and nitrogen gas. And then ketone or aldehydes you can react with HCN or KCN, which will generate the cyanohydrin. Reactions of nitriles, you can take nitriles in the presence of water under acid or basic conditions, generate the amide. Again, equivalent will generate the acid. In the presence of lithium aluminum hydride followed by water, generate the amine. In the presence of Grignards, form amine salt, and then followed by water, or protonated water will generate the ketone. And then in the presence of diol and protonated water will generate the aldehyde. Thioesters. So acids and alcohol will form an ester. If you use a thiol instead of an alcohol, the same thing will happen, right? Attack, electrons come up, this gets removed to generate a thioester shown here. In terms of resonance overlap in esters and thioesters, in esters they have good CO overlap. However, in thioesters they have poor CS overlap because the p orbitals are much larger. As a result, thioesters are more reactive towards nucleophilic acyl substitution than these normal esters. If we look at coenzyme A, this is coenzyme A actually used in a lot of biochemical steps in cells. It's a thiol who has a thioester shown here, and it's important in transfers with other nucleophiles in proteins or in the cells. Here's a nucleophile will attack, electrons will come out, form the tetrahedral intermediate, then electrons will come out and then release, right? So forming, having this acetate onto the nucleophile. So oftentimes you see like nucleophiles like lysine of proteins, like in histones, will get acetylated using acetyl coenzyme A. Carbamide esters. Carbamide esters can be generated from isocyanate and alcohol, in which electrons go and attack, go to the nitrogen to form the carbamide esters. These are some examples below. But also they can generate polymers. So here's phosgene and bisphenol A, so then you're going to have a reaction, right? Electrons come up, electrons go down, kick one side of it off, and then you can have another where you have these polycarbonates being formed. Problem with polycarbonates is these are plastics that are used. If they start degrading, you get bisphenol A, which is actually very hazardous to one's health, so one must be careful. And then polyurethanes, this is a toluene diisocyanate, ethylene glycol. Again, let's say one is going to go over here, and then you form covalent bonds between the toluene diisocyanide and the ethylene glycol to form polyurethane. So this ends part 2 of chapter 21.